In this section, we're going to be looking at how we can solve trigonometric equations using identities and also things that are familiar to us. So in general, how do we solve equations? Plain old equations with a degree of 1, or what happens when we have a quadratic. So we want to kind of tie things back to equation solving that we've been doing kind of ever since Algebra 1 and earlier this year. So we're just basically going to do a bunch of examples. So if you look at the first example, we want to find all the solutions of the equation. So that's important that we're looking at all solutions. We're not saying just between 0 and 360, but we want every single solution. And if you think about when we talked about this before, when we look at your unit circle or a circle in general, right, that makes a 360, but is there a solid rule that says we must stop after one rotation? No, we can go on and rotate multiple times and make 5 full rotations if we want. So we want to take that into account when we actually write our answer. So just keep that in the back of your head as we solve this, okay? So we want to solve for theta, okay? So what we want to do is we want to kind of like what you would do. Imagine this was an x equals 1/2 x plus 1/4. So kind of imagine that. We want to solve this equation, but in this case, x is the whole thing sine theta, and we'll deal with the sine at the end. So kind of long story short here, we want to isolate sine theta, so then we can actually calculate what theta is. So what I want to do is solve just like I normally would. So I want to consolidate all my sine thetas onto one side. So I'm going to subtract 1/2 sine theta to both sides. Because remember, sine theta, sine 15, right? Sine pi over 4, it's a value. It's a not so pretty number, but it's still a number. So we can add, subtract, multiply, divide by sine of some number. And theta represents a number. So we can subtract 1/2 sine theta to both sides. So 1 sine theta minus 1/2 sine theta gives me a 1/2 sine theta, right? This zeroes out, and then we get 1/4. Just like if this was a 1/2 x equals 1/4, we're going to multiply both sides by 2 by the reciprocal, right? So we can solve for just a 1 sine theta. So then sine theta here is equal to 1/2 when I simplify that fraction. And now is where we want to actually deal with the sine. So we want to think, well, wait, sine of what angle measure equals 1/2? And here's where you really have to think about, do I need to estimate this in the calculator, or do I actually know a value? So what I would encourage you all do is have your unit circles ready, because we can look, remember, sine is the y value of the unit circle. So we're looking, is there a y value equal to 1/2? So if you bust out your unit circle, we're going to say, well, yeah, there is. Y is 1/2 at 30 degrees. Y is also 1/2 at 150 degrees, right? Because sine is positive in the first and second quadrant. Now, these are the only two answers if we're looking in 360s, but remember, we don't necessarily need to stop. We could rotate again. And because sine has a full period of 2 pi or 360, we can go ahead and add a full rotation. So I'm going to say plus 360 times k, plus 360 times k, where k is an integer. So we're saying, okay, we start at 30, but we can also do 390, because we can go a full rotation from 30 and we'll still get sine of 390 equals 1/2, because think about those reference angles we talked about. Okay, does your answer here have to be in degrees? No, because it doesn't specify. If you would like, feel free to write your answer in radians. If we're going to do radians, right, 30 is pi over 6. Then remember, a full period here is 2 pi radians, so we can have 2 pi k, right? And theta here, instead of 150, you can write 5 pi over 6 plus 2 pi k. All right. So this next one, 2 cosine theta plus square root 3 equals 0. Same idea. If you want to pause here and try it on your own, go for it. Otherwise, I'm going to go ahead and walk you through this one too. Okay, so remember, think of cosine theta as what we're trying to isolate. We're trying to solve for cosine theta, and then we'll deal with the cosine at the end and think about what theta is. So I want to isolate this cosine theta by subtracting square root 3. So 2 cosine theta equals negative root 3. And then we want to get that cosine all by itself. We want to solve for a single cosine theta. So cosine theta is negative square root 3 over 2. And again, you might be thinking, wait, can I just use my calculator so I can do the inverse operation? But if you have your unit circle in front of you, check. Cosine, remember, is the x. So we want to see, is there a point on the unit circle where x is negative square root 3 over 2? And yes, there is, because remember, our 30, 60, 90 triangle dealt with that square root 3. So when we're looking at, cosine 30, cosine 60, we will see that square root 3. Okay, whereas cosine's negative in the second and third quadrant on that left side because we're going to the left, so it's negative. So I'm going to find here, let me kind of portion that off. Theta in degrees is 150. And remember, it can go in a full circle again and again, so we're going to add in 360k. Or theta could also be 210. And again, we can go in another full revolution or 2, 3 revolutions, however many you want. So I'm going to add that 360k. So k is an integer, which basically says, we're going to go in a full circle, right? Not half a circle, not a third of a circle. Again, if you want to do this in radians, go for it. It doesn't specify, so I would take either. Just like if this was on a multiple choice question, on a multiple choice test, you want to recognize both. So we can totally write 150 as 5 pi over 6 and add 2 pi k. And 210, if I look back at my unit circle, is 7 pi over 6 plus 2 pi k. So these, I hope, are pretty straightforward. So again, you want to isolate the trig function, so isolate sine, cosine, or tangent, and then figure out the theta after that. So you use your unit circle or perhaps use your calculator. One thing I want to mention, because we didn't do tangent here, sine and cosine both have a period of 2 pi if you look at the graph, right? That makes sense. It goes from 0 to 2 pi. But remember, tangent has a period of pi. So when we're looking at rotations for tangent, we want to go with a period of pi. There's a great example of this in your textbook if you want to look at that, where they do solve for tangent. But again, we didn't do it here, so just something to think about. The period for tangent is pi and not 2 pi. So instead of doing plus 2 pi k, we'd be doing plus pi k for tangent. Okay? So let's take a look at the next type of equation. We've got quadratic forms of trig equations. So notice now we're solving the equation for the given domain. Oops. I meant to highlight that. So we want to look at the given domain. So it tells us we're restricted to 0 to 360 degrees. So that tells us a couple things. That means we don't have to deal with adding on rotations, but this also is telling us, hey, I want my answer here in degrees versus radians, right? If you look at the next one here on to the right, we have 0 to pi. So we want to make sure we're only doing that 0 to 180, that half circle. But again, we want this answer here in radians. So make sure you're careful, look at that, because that tells you how to write your answer. And then let's go ahead and solve this. So you might realize, wait, quadratics, we've talked about quadratics a lot. And yes, we're dealing with quadratics in a very familiar way. Factoring, quadratic formula. The only difference is instead of an x, we're given the trig function. So remember, we're going to treat like tangent theta, sine theta as what we're solving for. So that's our x. And then we're going to deal with the inverse or figure out the theta afterwards. So let's take a look at this first example. 4 tangent squared theta minus 7 tangent theta plus 3 equals 0. Remember, because we see, okay, tangent squared theta, there's a square, there's a quadratic, right? That highest degree is 2. Make sure one side is equal to 0. And yes, it is. So what I want you to think here is imagine this as the problem 4x squared minus 7x plus 3 equals 0. Isn't that so much more approachable than if you looked at tangent? Because that's literally what we are going to do. But in this case, our x isn't just a number. Our x is actually tangent theta. So we're going to solve for tangent theta and then deal with what that value is at the end. Okay? So if I'm going to factor this, remember, using whatever method you like, try factoring, right? Hopefully by now we're really good at factoring, but if you want to do the quadratic formula, you totally could. But here, this is factorable, and I factored it pretty quickly to get the factors 4x minus 3 times x minus 1 equals 0, right? And now before you split this up and do your zero product property and be like, yeah, no problem, I can solve this. Remember, we're solving for theta. which is part of tangent theta. So what I'm going to do now is rewrite this where I'm putting in tangent theta for each x. So this is really 4 times tangent theta minus 3 times tangent theta minus 1 equals 0. And now let's do our zero product property and solve just like we were doing in the first example. So either one of these parentheses, these factors, could be 0. So 4 times tangent theta minus 3 equals 0, or tangent theta minus 1 equals 0. So let's go ahead and solve for tangent theta. So I'm going to add 3 to both sides. Here, divide by 4. So tangent theta equals 3/4. And here, just going to add 1 to both sides to get tangent theta equals 1. So remember, we're not done yet because we're solving for theta, not tangent theta. So I'm going to whip out my unit circle to see, is there anything I can get exactly from the unit circle? Well, I might realize, remember, tangent is y over x. So we want to see, where's y over x 1? Where would y over x be 3/4? Well, unfortunately, with this 3/4, I don't see it anywhere on my unit circle, right? It's really just not possible. So that means to do this, I'm going to use my calculator. So what I'm going to do is do my inverse tangent function to get inverse tan of 3/4. Put that into my calculator, and I didn't say where to round it to, so let's go ahead and round it to the nearest hundredth. So theta is roughly 36.87 degrees. Okay. Then moving on to the other side, tangent theta equals 1. Well, do I have a situation where y over x equals 1 if I look at my unit circle? And I totally do. It's where I have square root 2 over 2 and square root 2 over 2. So here I don't need to use my calculator because I can say, hey, theta is going to be at, and I want this in degrees, so 45 degrees. And also, if I look, negative square root 2 over 2 over negative square root 2 over 2 at that 225 degrees is also 1. So now before we box all of our answers, you might be wondering, wait, why were there 2 answers here for 1, but only 1 for this part that we did in the calculator? Remember, the calculator, when we do this inverse tangent, it gives us the acute angle, the reference angle. So what we want to do is we want to realize, wait a minute, there should actually be 2 answers for tangent because tangent is positive in quadrant 1 and quadrant 3 because it's positive over positive, negative over negative. So I'm going to do this in a different color, so hopefully it makes sense. So if we're thinking about tangent here, right? Tangent is positive here in the first quadrant, positive here in that second and the third quadrant. So if we're looking at 36.87 degrees as this reference angle, this is 36.87, we want to know what would that corresponding one be down here. Well, I didn't draw this super well. Let me try to fix that. There we go. What's neat about this is this makes a full 180 because we're just looking at kind of going straight across to that other side, right, of that arrow. So what I'm going to do is take this 36.87 and also add 180 to that. So that is going to give me, that should be approximately 216.87 degrees. Okay, so you want to realize here we have 4 different answers. And I know you might be wondering, wait, what? And that's because if we think about the quadrants, and that's where, if you remember, I mentioned this in class a long time ago, that all students take calculus sort of thing. We want to think about where is tangent positive, and tangent, everything is positive in the first quadrant. So we can see that's why it's positive here. And then tangent is once again positive in third quadrant. So we have 2 possible answers in 360 degrees. Okay, so that's where that comes from. Okay, so for the next example, we're going to do something very similar. So if you want to pause again and try this one first before you see what I do, go for it now. Otherwise, I'll start walking you through this one too. All right, so the big difference between the first problem, that 4 tangent squared problem, and this 2 cosine squared problem here is our answer needs to be in radians because it tells us that given domain in radians from 0 to pi. Also realize we're doing half a circle, so we only want to look at that top half, right? If you're looking at that unit circle. But again, when you approach it, you can think about this the same way. This 2 cosine squared theta minus cosine theta equals 1. Imagine this as 2x squared minus x equals 1, because to me that's a lot easier to approach. And I want to think, well, how would I solve that? I'm going to take away 1 from both sides because I want a 0 on one side of my quadratic, and then I'm going to go ahead and try factoring. And again, if you want to do the quadratic formula, you could, but this one's super easy to factor as well. So when I factored this, I got the factors 2x plus 1 times x minus 1 equals 0. And in this case, we're thinking about x as cosine theta. So once I get my factors, I'm just going to replace x with cosine theta, and I'll get 2 times cosine theta plus 1 times cosine theta, oops, I don't want to close out parentheses too early, cosine theta minus 1 equals 0. And then use your zero product property, and we're going to solve just like we solved those first two examples. So 2 times cosine theta plus 1 has to be 0, or cosine theta minus 1 equals 0. So let's go ahead and solve for our cosine theta. I'm going to subtract 1 from both sides there, divide by 2 to get cosine of theta equals 1/2. And alternatively here, just add 1 to both sides, cosine theta equals 1. And hopefully by now you recognize, oh, 1/2, 1, I've seen these on my unit circle. Let's go ahead and look. Remember, cosine once again is x. Where is x negative 1/2? And remember, we only want to look from 0 to pi, so that means we only care about that top half, this section, quadrant 1 and quadrant 2. So just look at that first half of your unit circle, and where do we see negative 1/2? I see it exactly once, and that is at 120 degrees, but I want my answer in radians, so I'm going to write that as 2 pi over 3. Okay? Now, where do we see x equals 1? Again, just on that top half. Well, here, it's right at the very beginning where theta equals 0. So those are my answers. So the number of answers you get will differ depending on your domain, because we were looking at the full 360 for the earlier problem with tangent. We had 4 possibilities. Okay, here we only have 2 because we're restricting it just to that top half. Okay, let's keep on going. So now how can we use trig identities to help us? So we're kind of just combining a lot of ideas together here. All right, so hopefully you guys have your trig identities handy. So when I do these problems, my first goal is to not have 2 different trig functions in the same equation. So if you look at this first example, tangent squared theta plus secant squared theta equals 3. I want everything either in terms of tangent or in terms of secant. I don't want to have 2 different ones on there, because it's like saying, how do I solve an equation where I have an x and a y in the same equation? You can't unless you get a second equation. And here we only have 1 equation, so we need to basically come up with our second equation using a trig identity, and then we can solve with substitution. So you want to whip out your trig identities again, and you might realize, hey, we've got an identity here that we can use. It tells us that secant squared theta is equal to 1 plus tangent squared theta. So what do you know? I can take this 1 plus tangent squared theta and substitute it in for secant squared theta. So I can rewrite this using substitution. So tangent squared theta plus 1 plus tangent squared theta equals 3. And that becomes so much more doable, right? It's basically saying, how would you solve x squared plus 1 plus x squared equals 3? We can solve that. Now remember again to look for those domain restrictions here. We've got 0 to 2 pi, so we want to make sure our answer is in radians, and we are going in a full circle from 0 to 360. Okay, so let's go ahead and solve. So I can combine my tangent squares to 2 tangent squared theta plus 1 equals 3. And then I'm going to subtract the 3 to both sides, because when I'm doing a quadratic, I want a 0 on the other side, so then I could potentially factor. So I have a greatest common factor here of 2. And then I have a difference of 2 squares. So if you've forgotten, this is that a squared minus b squared shortcut, where we get a minus b times a plus b. Here a is tangent theta and b is 1. So my factored form is tangent theta minus 1 times tangent theta plus 1 with that greatest common factor of 2 right up in front. And then we can go ahead and solve. And if you wanted to do what I was doing before and replace tangent squared theta with x squared, you could. Just make sure you put that tangent theta back in as you're working. Okay, so we're going to ignore that 2 because 2 is never going to equal 0, right? So 2 is kind of on its own, but we know tangent theta minus 1 could be 0, or tangent theta plus 1 could be 0. So what I want to do is find theta so that tangent theta equals 1, or tangent theta equals negative 1. So again, look at your unit circle. We're going to be going a full 360 degrees. So where do we see 1? So remember again, tangent is y over x. So we're going to look at that square root 2 over 2 part. So tangent theta is positive in the first and third quadrant. So I'm going to see, okay, well, theta could be at pi over 4, or theta could be at 5 pi over 4 here. Where's tangent negative? Well, that's in the second and fourth quadrant because we'll have a positive and a negative. A positive or a negative, or a negative or a positive. So in this case, we're going to get 3 pi over 4 or 7 pi over 4. So this problem gives us 4 possible answers. Cool. All right, one more using identities. And again, if you want to pause and try it on your own, because obviously I can't do every single different combination for you. So reference your identities and see if you want to try that out first. So pause right here if you'd like. Otherwise, I'm going to keep going and show you how to do this next one. Okay, so once again, what I want to do is I want to write this entire equation either in terms of cosine or sine, but not both. So I'm going to go back and look at my trig identities, and I'm going to find, hey, there's one handy one I can use. Cosine squared theta plus sine squared theta equals 1. So what I can do is I can either solve for cosine squared theta or sine squared theta. It really doesn't matter. It's your choice. And then replace the cosine squared theta or the sine squared theta of the original problem with the equivalent expression. I'm going to go ahead and solve for cosine squared theta. So I'm going to subtract sine squared theta to both sides. So I'll get 1 minus sine squared theta, right? And I'm going to take this expression, this 1 minus sine squared theta, and plug it in to replace cosine squared theta right there. So then I'll have everything in terms of sine squared theta. Now, if you wanted to solve for sine squared theta, go for it. Your equation is going to have all cosines. It won't matter because you should get the same answer. Okay? So, oops, sorry about that. So I'm going to rewrite this now as 1 minus sine squared theta equals 1 plus sine squared theta. And just like always, when it's quadratic, when we see that square, we want to get one side equal to 0. So I'm going to subtract the 1 and then add sine squared theta to get 2 sine squared theta. We can divide both sides by 2, but 0 divided by 2 is still 0. And then we can square root both sides here. And what do you know? Sine of theta equals 0. So again, sine is y. Look at your unit circle. Keep in mind our domain. We're going from 0 to 2 pi. Where is y 0? Y is 0 in 2 locations. At 0 and pi. And again, I'm writing my answer in radians because the domain is given to me in radians. Okay? So that's it for all the examples I'm doing with you, but I'll have the next video with the U-tries. I do encourage you to look at those U-tries. We haven't done a double angle problem, but there is one in that U-try. And we didn't do one earlier that required the quadratic formula because it didn't factor, and I'll have one of those in the U-tries. So if you're interested, feel free to watch that optional U-try video. But of course, you can try the problems on your own first and then double check. All right, let me know if you have any questions.